got a lot to say. Limited amount of time. Okay, why linked lists matter as a data structure at all? So, in computer world, language, whatever, you have types like ints. Ints are said, they're telling the computer, I'm creating an int. An int takes up 4 bytes, right? So the computer can go out there and say, I need to mark off 4 bytes for whatever this person's going to put in here, whatever this program's going to put in here. But it marks it off, right? It says, okay, these 4 bytes, I can put numbers in here. Because it's unsigned, it's negative 1.1 billion to positive 2.3 billion, whatever the numbers are, right? That's an int. So whenever you have contiguous memory, like an array, it says, oh, okay, so you want 5 ints in this. It marks that space off first, right? This is how computers work. It says, okay, so you want 5 of these, right? 5 of these. So I'm going to mark off this big chunk, and I'm going to have 5 different, each one of these is an int, right? Now this is cool because when you do an array, it's super fast, right? So the computer knows, oh, data, really fast, right? But that's because we know the size of an int. We know it's going to be 4 bytes each. What happens if we don't know the size? Uh-oh, now we're in trouble. That's where a place called the heap comes in. That's this big chunk, big chunk of memory, basically all of your memory that's not dedicated to something else. Big chunk of memory that says, hey, you can throw as much in here as you want, as much as I've got, right? So when you create a new object, it just says, hey, out there in the heap, I have an object. And it's of whatever size, right? I can create a bunch of these. They're in no particular spot. It's all cool, right? But if we want to make a list of this, how are we going to do that? Because we don't know the size. We can't make an array of it. We could make an array of it. What if it wants to change? What if we want to add one? So in an array, if we have 4 and we want to add a 5th, we're in trouble. Now what we got to do is we got to create another array, because remember, arrays are fixed size. They can't change. We got to create another array of 5. Whoops, that one's nice and pretty. You got to create an array of 5 and then copy everything from this one to this one to this one, right? And then add the other one. Man, you want to talk about lack of optimization. That is slow and crappy. By the way, that's why strings suck. Strings are just character arrays. Whenever you create a new one, yeah, it sucks. So really slow, right? But for accessing data, if you need to do it really, really fast, arrays are cool, right? Super fast, dip, 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 right? So now in comes linked lists. What linked lists allow us to do is create what's called a node, right? The node is just an object. I mean, in fact, it doesn't have to be called node. That's just the normal term for it, a node, right? You have a value, which is, whatever. Let's say our value is ints in this thing. So we have value like 1. And the only other thing you really have to have, at least in a singly linked list, is a pointer to something else. Maybe a bad term because there are such things as pointers, but basically we just need a reference to the next one in the list. So we're going to have that next. Okay, and it is going to be of this type as well. So this is node and this is int, right? Now the cool thing, the reason that linked lists are cool is because if we create one, but then, later on we're like, oh, we need to add 2 more. Oh, well, we're out here in the heap, right? Out here in as many objects as we want, throw them out there, fill it up, right? So we create another one as value. We're going to put v and in. You guys know that's value next. And because we point this next over to this one, now we have an item that we can go through. And let's say somewhere else we create another one. Oh, here we got another one. A V and an N. Okay, cool. We want to add this other item. Again, this is floating out in la-la land, right? We can create as many of them as we want. That's why it's cool. Point this one to this one, Now we can just hop through them, just like an array, sort of,
Don't
right?
they point both directions?
In a doubly linked list, you can. We'll get to that. This is a singly linked list. Okay, so add another one. We're all good, right? D and N. Point over here. Now we can just say, hey, give me 1. Pop. Give me 3. Pop, pop, pop. Boom. Right? Cool. Now we have like infinite numbers. Now, that's really good because adding and removing from a linked list, super fast, right? Say I want to get rid of this one. All I got to do, remove that pointer. Set my head to this one. Boom. Now, this one just gets taken by garbage collection or whatever your compiler does with it. Gets rid of it, right? Now we have a list of 3. Want to get rid of the end? All we got to do, get rid of where this one points. We don't even have to, we don't notice we're not getting rid of the data, right? We're not getting rid of this. We're just saying nothing's pointing to it. And because it doesn't have any reference, garbage collection will eat it up. Super fast, right? You're not even deleting data. You're just getting rid of where it points to. And because it points to nothing, gets rid of it. Notice my list is still here. I still have 2 elements that I can still bounce around in, right? This one and this one. So super fast for adding, because adding, you just point it to the next one, right? Super fast. Removing, super fast. Let's say we still have these connections, right? We got our list here. Let's say we want to get rid of this one. You think, oh, well, we got to get rid of this data. Nope. All we got to do, point this one to this one. Notice our chain. That was just floating off. It's gone now. So deleting, stuff like that. Now, that's really good if you need it. So linked lists, really good if you need an infinite size that can grow quickly, right? Not like an array where you got to copy all the things over to the new size and guess the new size, and, right? So very, very good on that. Now, why is it slow to traverse? Because
So what, sorry?
to traverse.
What does that mean?
So if you want to go through an array and you want the 6th element, all you got to say is array the 6th element. It immediately knows. 01, right? 01 operation. The 12th, the 5,000th, the 10 millionth element. Doesn't matter. It's an 01 because it knows exactly what element to go to. You don't have to go down the chain. Linked list is slow because if you want to get, remember, the only things that node have is whatever the value is and what it points to next, right? It doesn't have every one of these in the thing, and as you can imagine, that wouldn't make a lot of sense to have. Right. So if you want to get to the 4th element, you have to go to the start, go to the 2nd one, go to the 3rd one, go to the 4th one. You have to do all the hops. And if you have 1,000,000 elements to get to the 900,000th one, that's right, you got to do 900,000 hops to get to it. So traversing is very slow. And if it's a singly linked one, you have to go forward. You have to start at the head and hop all the way through it. So traverser, if this algorithm is that you're building using this data structure, it needs to be able to search for stuff fast. Linked list is not your, you need to add and remove quickly. Super good. What's up?
Can you implement an index with the memory locations of each element to like cut time for traversing, or?
You could, but you're going to have a massive. You're going to have you'd have to essentially have an array that you're adjusting, right? Because again, you don't know how many elements you're going to create or how many you're going to have, or if you're going to add one later. So that array that you would be keeping up with, whatever the index for each thing was, that would be not only massive, but you'd be creating an array. Might as well use an array in the first place, right?
Defeats the point of having.
Right, exactly. So, yeah, super good for stuff like that, right? Now you know the why. So, everybody good? Any questions?
If you have 2 linked lists, can they share elements?
Well, actually, I mean, sure, because technically it's all pointers, right? You could have 50 things pointing to, to this as an element.
Mm-hmm.
Now, this one is still going to only point to its next, but it doesn't really matter because they're all just references, right?
If you change it in one node, does it have to be the same element in all of them?
Well, no. But so if you had, let's just say you had random whatevers, and they're all pointing to this one, right? If you change where this one points, obviously that's going to change it wherever. Because again, remember, this is not data, just pointers. So you could have a lot different of things pointing to a, in fact, there's probably some fairly complex data structures that utilize that ability, but it would have to be pretty complex.
Well, plus every element down the chain would be the same for all the linked lists because...
Right. But let's say you wanted 5 lists that start somewhere else and then go to the second element of this one. Totally do that. So, all right, cool. We are, now just to give you an idea of what Scott asked a minute ago, there are different kinds of linked lists. There are some that hold more values and so on and so forth. One of which is called the doubly linked list. Same exact idea, except for you have basically a forward and a back, right? So when you create a new element that you want to point to, BNP, you point this one to this one, and you point this one back to this one, right? And then when you create a new one, the idea is that you can move forward and backwards. Because if you go to this element and you say, hey, let's go to P, P is going to go back to this one, so on and so forth, right? If you add a third one, and you want to now this one to become forward, you'd have to remove this pointer, point this one here, this one, because this would, probably should do it next, but anyway, this one would point here, and then this one would point here as well. So you get that. So basically you can traverse forward and backwards instead of straight through. You might think that this is always, oh yes, why not, right? Why not always have this? Remember, the idea is to have linked lists is to have this very low resource way to manage data, right? So you're adding yet another reference that has to be kept up with. Every method that you call has to, let's say you delete a node, well, now what? Not only do you have to point this node to this one, but this one to this one, right? So it's more overhead, and and it does require yet another reference in every single node that you create. So it's kind of if you need it to be forward and backwards traverse, then cool, but if not, then don't do it, right? You only use what you need. So yes, linked lists, very cool because you can add 1 billion of them. Don't have to set any limit. Don't have to set it when you start. Your program can create objects on the fly and add them on the fly. Just remember that traversal is quite slow because you have to do all the hopping to get where you are instead of the direct place, right? Everybody also understand the benefits of that over arrays, right? Arrays are fixed size. By the way, that's not a C# thing. That's any language. That's a computer thing, right? You have types that say, I need this much memory reserved, and if you want to kind of dip into the CS reason of why, think about when you create something that holds a number, right? Let's say it has 4 slots, right? 4 bytes. And by the way, there are languages where you can do this. A lot of hacks come out of stuff like this, is that if you could overrun that, right? If you could say, well, I only have 4 bytes here, but I'm going to add 5 things. If you could do that, you are now overriding other memory. Well, obviously, you don't want that in computers, right? Like, oh, well, now all of a sudden now half my operating system is overwritten because now this, you know what I mean? Like, that's a bad thing. So that's why, like, there's a thing in programming, type safety, and that's kind of an important thing, lower level languages, assembly and C and stuff like that, they don't have those restrictions. You can totally try to write across, whatever memory slot you can, but that comes with some cost too, and that's a bad thing. You don't have to worry about that with stuff like C# and Java and
To
whatever.
the programmer to police that in slower languages.
Yeah, well, I mean, it's I would say there's uses for it, but because I mean, there's back in the old days before we cared whether we were downloading 2 megs or 500, whatever. We didn't. Now it doesn't really matter how big things are. So whenever we want to update a program, we just download the new program and install it, right? Like, who cares? But in the old days, whenever it was really slow to download things, when your program got a bug or they found some bug, they there was like, oh, well, we can't just ship this new CD. That's like 600 megs. That'll take forever for anybody to get a patch. No, so what they do is they'd send a little tiny program that would overwrite your executable or whatever part the bug was, and then ta-da. That's why in the old days they called it patching. That's literally what it was doing, with patching, whatever. So it's useful. It's just understand why linked lists are good when you get out there.
Did you think of a common example when updating your list quickly is really important, but accessing the data quickly is not so important?
Lots. So imagine you are building something that requires data. I mean, say you're pulling information out of like a database or something like that, right? First of all, you don't know how much it's going to be, right? And you certainly wouldn't want to create a new thing every time it came up something new, right? And you need to be able to add and delete stuff quickly, right? Like, so say it's like a revolving customer order thing, right? So as they go out, you need to be getting rid of them quickly, right? So you can totally add and remove off the ends of these really, really quick. Very good, I mean, it's another data structure just like queues and stacks and so on and so forth. Each one of those is sort of a varying rule of this, right? So yeah, being able to add and quickly, especially off the end ones. Even removing the middle things, it's very quick. Now, you have to remove the 5th element or whatever, you'd have to traverse down and then set the next to that one's next, right, to get rid of the one. But, so that's why, like, again, traversal limit. But as far as, like, say you have something that's adding and removing stuff off, elements off the end real quickly, or do you just need to be able, imagine you're writing some kind of buffer, right? Like, you're going to receive way too many objects for you to process and deal with, right? But you don't necessarily want to lose that or to even to asynchronously. No, just get it all in, create more and more and more nodes for this, and we will, as we get them, we will cycle through. And think about that. I mean, even as a queue, if I'm constantly going to the head, right? Whatever the head is pointing to, but every single time I get one in, all I got to do is remove that pointer. I don't have to delete any data. I don't have to just remove that pointer. That's it. Super duper fast, right? This thing's gone. Now the next one's going. As it goes. As I get rid of more orders. Right? Okay? I'm not getting rid of data because the computer's going to do that for me. All I'm doing is just dereferencing this thing. It's super duper. It's way faster than trying to actually delete data, right? Yeah, bad stuff. So. Yeah, there's quite a few uses for it, and whatever. We'll do good. So I'm just going to walk through this. I think a lot of people are stuck, but at least you can see me do it, right?
I finally got it. It was
right.
just downloading some dependencies.
Yeah, it's crazy, man. Okay, so we're just going to go ahead and get rid of, I guess we'll leave program. We'll maybe do some test stuff in here. By the way, I am sorry because this is ginormous out here. But, all right, let's create us a new class. We're going to call it, what are we going to call it, David?
Linked list?
Well, we're going to call it node,
Oh, node.
right? We need some object, and what is that node going to have?
The value, pointer to that.
That's right. That's absolutely right. So we're going to create us a new class. We're going to call it node.
But you can use this in
And by the way, you'll notice I also don't use VS Code as much, so some of the keyboard shortcuts are a little bit different than Visual Studio. Yeah. Now, okay, so we're going to make this one of ints just because it's easy, right? So we're going to do, by the way, you're going to see me make this public variable. If you do C#, don't ever in your life make a public variable. Don't do it. I'll tell you why later, but don't do it. This is just for demo purposes. You ever seen me do this in practice? Shame me. All right, public. int value. No, we are going to create a
Delete program.
public. What type should this be, David? What are we pointing to?
It's an address.
Well, it is, but what are we
And then
pointing
this is
to?
just what when we created the file.
The next node.
That's right. So what type does this need to be?
New node.
Node.
No.
Needs to be type node. Right. And we're going to call it what? Huh? What are we going to call it, David?
Next.
That's right. Man, look at this guy. Ha. All right. And then we're going to make a quick constructor just because we are going to force whoever creates a new node to do stuff. Actually, we'll just, since we're leaving this public, we'll leave this on. All right, cool. We got us a class, guys. Right on. Called node. Has a value of an int. Takes an int and node next. By the way, just because I think from talking to a lot of people don't understand this. This right here, this type, int, node, whatever, that is not doing anything except for restricting whatever your variable name is to whatever this definition is. Meaning, this can only contain ints, right? And this variable next, it has to have an int and a node, right? So the reason I mentioned that is because on the other side of the equal sign, when you do new node, now you're taking a copy of this, but your type is node, not your implementation, right? So if I put a method in here called, I don't know, whatever, do something. Now everything that I make that is of type node has that method, right? So it is important to distinguish the type definition as opposed to the type implementation. You'll see what I'm talking about later, but just know that that's kind of important. I think a lot of people think those two things are the same on the other side, it's very different, it's important. All right, so we got us a new node. That means over here, let me fix this terrible Microsoft formatting. Worst thing Microsoft ever did, almond. Don't do it, it's terrible. I know you JS guys, we see eye on this. All right, we're gonna create us a new node, right? Node. So, just so you know, convention, the thing that always points to the start of your linked list, convention is named head. I didn't make that up, but it is. And it kind of makes sense. This is the head of your linked list. You can name it whatever you want as usual, but normal convention is call it head. All right. Now we need to create, just to start to populate our list, right? We're going to say, give me a node, we're going to call it current. And we're going to create a new node. And let's just for demo purposes, let's force our constructor to populate our stuff. That way we don't have a bunch of floating whatever around, right? So we're going to say int value node. Oh, no, we're going to say int value. How's that? Anybody want to earn bonus points? David does. Look at him. He loves it. Why do I say this value equals value? Should know this from JavaScript as well.
So you're talking about that specific object.
I'm talking about, well, that's sort of true, yes. I'm talking about this class's value. So this is pointing to this. This value is pointing to the one that I passed in here. So if I pass in a 10, it's saying, okay, this is 10. This is why I was saying it's important to know that the other side of the equal sign is not the same as this side, right? So right before this does anything, this is null, because it doesn't have anything. This is 10. Now it's saying this 10, set it to this, right? So, important. You'll see. So wait till you get into dependency injection and stuff, you guys. I promise you, stuff like that it matters, right? Because your type that you define can be completely different than the implementation that you assign to it. It's just going to be limited to whatever that type definition is. Everybody got this? David, you good? Yeah? All right, cool. All right, so all that means is that when we create a new node, we have to give it some kind of value. You don't have to do that. I mean, I could do it outside of that if I wanted to, but, you know, kind of pain. But, all right, so we're going to assign our first node 1, right? Cool. Now, we're going to create a new one, a new node. And we are going to point our current node. Wait, before we do that, to make sure we always have a starting point, this is our first node, right? We want to make sure we point head to that. And that's going to stay there. That way, no matter what, we can go back to head and traverse through our list, right? So the first one, we're gonna do. Oops, sorry again. Hi-yo. Current. All right, man, look at that. You're making some good progress. All right, we have a node that has a value of 1. What does node next point to? Anybody? Right now, in this thing, what does node next point to?
No.
That's right. It's null. Currently null, which is cool because how do you know when you get to the end of a list, how do you know you're at the end, right? You're always just going to the next one, right? As you hop down the line, next, if there's next. So how do you know? That's how you know. If your node next is null, you're at the end. Voila. That's also why if you remove the pointer to the last one, you get rid of that element, you don't have to delete that last element. Now that the next to last one's next is null, so that's the end of the list. Ta-da! You're going to love this. It's going to get really confusing in a minute. All right. So now we have one node, and node next is no longer a thing, right? So let's create another one. And we're going to do that by saying current next equals new node. We're going to give this one 2 because we are really smart. Cool. All right. Now, so if I go to head and say give me the value, what's this going to print out?
1.
That's right. Now if I say cool, now head equals head dot next.
It's going to give you null.
No.
Wait, no, it'll give you 2.
Well, if I do dot value, yes, it will give me 2. That's right.
It'll
That's
jump
right.
to the
Yes,
number
it will
2.
go into the next one. That's exactly right. That's exactly right.
Because
You
you
guys,
added it.
you guys are
and
getting
then-
this right. I just
you-
think it's So that's great.
But then if you did it again, then it would go to null.
That's right. All right, let's just create a couple more here, just cause. So now we're going to current. What's current? Next. And now we're going. You see what we did there? Same pointer, right? So now where's current pointing? What value does current have currently? That's right. You can say it. You don't have to sign it from the back. We're all good. That's right, too. That's right. So, what about head? What's head equal? What's the value in head? That's right. Man, these guys are smart. All right, let's print this out. So, if we want to print this out, can't just for it, right? Because we don't have an index. What we can do is say while. Let's create us just a hopper here, something so that we don't break stride. Node, hi-yo. We're gonna say, what do we want to call this, Scott? Spot. How about 8 for iterator? Terrible name. It's not really an iterator, but we're going to call it it just in case. Just because. All right. This is just so that we can keep up as we hop down the line. Right? So, while
You've got an error with your it. Doesn't it need a semicolon or something?
it does, sure does. That.
So you're basically creating a new node object without.
I'm not creating a new node object. I'm creating a new variable of type node.
Or a new node.
See, but that is important. Again, guys, remember, until it is created, until the object is created and assigned to this, it doesn't have anything. It's just of type node. It doesn't have anything. So now I'm pointing this to the head, right? So we're going to hop through this and say, all right, so while it not equal null.
Wait, but don't you have to create a new one? It equals new node first or no?
No, I don't. We don't want it to actually. We don't want to create a brand new instance because we don't have a value to put in. All this is just a pointer. You'll see. Hold on.
So I'm confused though with the new construct.
Yeah, new literally means that's how you create an instance of that object.
So for it, is it referencing the current instance?
Nope,
Or
it
is
doesn't. It doesn't reference anything yet. It literally just says, "I need you, the computer, to take a chunk."
of memory?
Right. But currently it doesn't do any of that, right? Because it doesn't. It's just saying I am of type node. I don't have any implementation of node. I don't have any variables. I don't have any reference point. I have nothing yet. I'm just saying anything that comes into this variable name has to be of or a derivative of node, right? So nothing. It has nothing now. The computer doesn't even really know about it except for it's a reference spot. And you're going to see us hop down the line. You'll see why this is important. So
I'm trying to understand. So because, see, I don't understand how you're creating it without using the new.
I'm not creating it.
So
I'm just,
what is it doing? When you
it's
say
nothing.
it equals head,
Right. So head has something in it, right? Because head points to the very first node that we created. So it actually has, it is
shouldn't
pointing
it be
to it.
current dot head?
Current dot head. No. No. These both are reference points, current and head. All we're doing when we say head equals current is they are now pointing to the same object.
Oh, I see. Because you never use new with head.
That's right. That's absolutely right.
You just use new with current.
Right.
So you've only got linked
two nodes.
list.
I only have two nodes, and right now in my linked list, head points to this first node, and if you wanted to get to the second node, you'd have to go dot next.
And you're doing all of this so that you can start it, linked list item, the first item, to scroll through it to print out.
Right, because you can only start from the beginning. That's right.
So could you do head dot next and that will point to node 2?
You could. And the only problem is, and the reason, in fact, the only reason that I'm making a brand new node to skip through the line is because you don't want head to leave the first node, right? Because you need, if I removed head, I would have no idea where this linked list, there would be no reference. There'd be however many elements just sitting out in memory. And there's no way to get to it, right? Because I don't have anything that points to it currently, right? So that's why you leave head at the beginning. Now, if you get rid of the first element, you will point head to the second element, right? Like you dereference that. That's how you would get rid of the first element. But you still need something that points to the very beginning of this line. All right, and you'll see when we hop down through this why it's important to have this other node thing. So we're saying so right now at this line, we know just from the above ones, it now points to this one, right? Node 1. The first node, it says 1, right? Because head, we pointed it to current, and then, so both of these have the same reference point, and now both of these have the same reference point, which is the first node. First node. So, while it...
How does it know this though? How does it know to reference current?
It doesn't. So, here, head and current are the same, right? So if you did head dot value at this point and current dot value, same thing, right? Because they're the same. They're at the very beginning of the list. I come down here and I point it to head as well. So now all three of those things are all pointing to the same spot, which is this.
You're basically creating a fixed linked list that you can't.
It's not fixed though, because if I add a new node, I can totally tack it on the end and keep going. You're gonna see. Just
Yeah,
hold on.
but it's not something you could do on the fly. It has to be done in the.
That's right. If I wanted to add node 3 to this, because I wouldn't know where current was at, I would have to hop down the list to the end and add it there. You're right. Or if I wanted to go in the middle, right? Like if I wanted to add something between 1 and 2, I would have to hop down to node 1, and then I would have to point node 1 to the new object, and then point the new object to this node. And then we'd have 3, right? So let's print this out, just so you can see it hop down the list. Okay? So while it is not equal null, which it won't at the beginning because we have 2 in the list, we're going to console write line, it dot value. All right, cool. Now that's going to spit out the first one, but if we want to see them all, we got to keep hopping, right? We got to keep hopping in line. So what we will do is we will set it to whatever is in it dot next. I know this part usually throws some people because you're like, what? You're pointing that object to something that's in that object, right? Little bit of a mind mess up, right? But understand
It's just
that
like doing.
this next dot next points to this next node, right? So all you're saying is currently it is pointed here at node. I want it to point to whatever that dot next is, which happens to be this. So now it is down here.
Is there plus plus notation or something for this?
No. You mean to go to next? No.
Yeah.
Well, no, because all of this value and this next naming scheme, that's all convention, right? You could name that variable anything that you wanted. So.
Yeah, so
Yeah.
next
No, but-
isn't something. It's
Right.
just a name. It's
Right,
not,
exactly. It's
not
just
a
that variable
property
name.
or something.
And you couldn't increment node,
Yeah.
right? Because it's not a value type, but you couldn't increment. It's not like a 1, 2, 3, whatever. In fact, if you want, we can even do this just to kind of, maybe you guys think this is sequential. Let's say this is 69. So now you see it's not the first and second and so on and so forth, right? All right, so let's see if this runs. Anybody see any compile errors? I don't. Let's find out. There it is, spits it out right here, down here, right? It's hard to see as well. But hopefully. So, do you see what's happening here to spit this out? So it's coming down and it's saying, okay, it equals head. So I know it's pointing at the very first of the list, the linked list. You have 2 nodes here. It's coming down and say, okay, well, I know that it isn't null, because otherwise it wouldn't make it to this line, right? This while thing says, as long as it doesn't equal null, keep going, right? So I know that this isn't null. So I'm going to spit out the value of it. Then I want to set it to whatever is in the next, which remember next is of type node. So we built this out like this. We're going to add some more eventually. So what we have here, we have one node, v equals 1, and the next is points to the next node, right? So this node value is 69, and it points to nothing, right? So this node points here. This one points to nothing. So when it comes in, the variable it comes in, it says, all right, I know I'm pointing here. Spit out the value, 1. And then it says, all right, now set it to whatever this is pointing to, which happens to be this one. Oh, now it is down here. So when I say, all right, well, it's still not null, right? Spit out the value, 69. And then it says, oh, but now next is null, so I can stop. Now, you think about adding. If your program runs for 6 days, and then you find out, oh man, here comes some more data. Well, no worries, because even though this isn't sequential, I can totally make another one. And then just point this one down here. Whee, look at that, still works. That equals 420. Just a random number. So let's do that. Actually, let's get a little crazy with this. Let's do a bunch. Anybody? Wait. Let's pause. Questions? Is anybody following this? No, I mean, is anyone following this?
I got you.
Yes. All right. Hey, that's better than I expected. Jonathan's got to look at it. Came in late, already knew everything.
I keep getting errors.
You getting errors? What kind of errors?
Hang on, no, not right.
All right, cool.
I forgot to assign it to head.
So yeah. And again, you obviously would not go through making your nodes this way, right?
I am curious about. I know that for clarity you did it the way you did it, but could you put node it equals head as one line, or do you have to separate that out?
No, you totally could.
Okay.
Yeah, no, you totally could do
So you
that.
need to open your extensions list? You need to
The
install
reason
the
I did that was,
To clarity.
well,
Clarity.
remember I that this equal sign didn't do anything but do the assignment of
Correct.
whatever was on the right side, right?
Correct.
So if I threw up a new node, then it would equal some new node that I created, right? But right now it doesn't equal anything, which is important
Yeah.
because I don't want it to equal anything. That's all I'm gonna use is to hop down the list. Let's make a bigger list. Let's do this a little programmatically. All right. Node current. Node. 0 because cool. All right. Now let's do a for loop. Oops. I'm not good with the laptop, man. I use my keyboard. Let me fix it all.
What I did was
Let's do this.
for the package I installed.
I'm gonna create a bunch of these.
Did you click on it? You go down.
All right. So for each one of these things in here, we want to say current next equals new node, and we're gonna assign it I. Just to be a list of.
How do you do a random in C#?
We'll do it if you want.
I was just gonna say it makes it clearer instead of having
Yeah. I just wanted to make sure people understood during the printout that, you know.
So how does it keep track of the node, the stuff stored in the linked list versus the linked list number?
How does it keep track of? Come ask again.
Well, like in the previous one, you had 1 and 69 as the values, right?
Mhm.
But that wasn't the ID of that node. That
Right,
was
that's-
node
that's
0
kinda why
and node 1.
Well, sort of. I mean, it is, but you kind of can't think of linked lists like that because we're adding and removing nodes out of there is like this, right? So it's not like moving or removing an element. You are getting rid of the node, but it's not like you hop down to whatever has the value of 6 and then do it that way, right? It's like that number of hops down.
Yeah. But I'm just saying the number of the item, because it's keeping track of the number of the item in the linked list. Otherwise, it doesn't know how many times to hop down, does it? Oh no, it doesn't. It's just looking at the
Whatever's next.
It's just looking at the
Yeah,
next.
it has no
it's
idea.
Not looking at this item.
That's kind of the beauty of this data structure is it has no idea. At any point, what else is going on in the linked list? It has no idea, right? All it knows is what value do I have and what do I point to?
The only one
That's
it
the only
actually
thing.
ever keeps track of is the head.
Actually, yeah, the head stays at the front, and even that is volatile, right? Like I said, if you want to get rid of the first element, all you do,
If you change element,
just put head to the second one.
if you
That's
change
it.
the fifth element to head, then the first 3 or 4 are gone.
That's, well, yeah, sort of. I mean, you would want to dereference the one before that too, just because otherwise it holds reference. Your garbage collection wouldn't get it, but
Because the one before it would point to the
right,
new head.
still point to it, right? But yeah, no, but I mean, you're right. So yeah, it's real quick. So let's what is this going to give us? 19 something or other. Let's throw this out here real quick and just oh, well, let's do this too. That's not right. Let's get a little bit pretty with it, I guess. That won't be perfect, but that'll be very minimal. Really bad at this. I'm just putting this to where to spit it all out. Errors? Yeah, see, I don't know. Can you guys see back there? Sorry. Anyway, there you can see our linked list. So now let's say we want to get rid of a element, right? Quick and easy way. In fact, you know what? Guys, to make this a little bit easier, let's do this. Let's move this down here to its own. List. God, I am so bad at this keyboard. Let's see if that works.
So I wonder why did I come up with element 0 twice?
Because you set your I to 0 instead of 1. You went back in and changed it.
Oh.
Let's make sure this works. Perfect. I just moved print list down to its own method so that we can call it more than once without typing it. Remember, never repeat yourself, right? All right, so we did this, and let's set head to equal head.next. And then let's print the list again. What's it going to do, Tony? What's that going to do? I'm setting head to head next. Right now, this is our current one, 0 through 19. Head to head next. Anybody? Anybody?
Should it go to null?
It might, but what's it going to print out? What
It's
through
going to
what?
start at 1 instead of 0.
Man, look at her. April is on point. Let's see if I'm right. Look at that. That's the second printing. Perfect. Anybody know? Everybody know why? Head
Because
is
you
currently
advanced.
pointing to 0, and its next is pointing to the 1, right? When I say 1, I'm talking about the node that contains 1, right? So all I'm doing by saying head equals head next is now the one that was pointing to 0, I'm pointing that to the 1. So that's why. And again, remember, all this does is start wherever head was, down, right? So after I set head to head next, I no longer have this node. And that, again, is why it's so fast. I didn't delete that node with 0 in it. I just said, now it's no longer referenced. Think about how much faster that is than to try to actually delete the data, right? And I'm not saying the data doesn't ever get deleted and garbage collection eats it up or whatever later. But the point is you dereference that, now it's so much faster than trying to get rid of stuff. But now here's a question. What if we wanted to get rid of the second element instead? We're going to get rid of this head equals head next so that we're back at 0. But what if we want to get rid of the next element? How are we doing on time?
It's 7:03.
All right, we'll get through this part. Yeah, let's say we want to get rid of the second element.
Yeah, it's curly braces.
What do we got to do? We know we have to traverse first, right? We have to get to, because you can't do anything in a linked list because it's not an array. You can't just access elements, right? So if we want to get to the second element, we have to hop down there, right? So just so that we, a little hopper, equals head, just for equal. Now we're going to hop down this list, right? Mm-hmm. So, what did we say? Element 2, it doesn't really matter. But we're going to say, let's say we want to.
Would be hopper.net, would be head.next.
Right. Well, if you wanted to go directly to that, but you don't know. I mean, yes, we know in this example we want to get rid of the second one, so that'd be really quick. But if we didn't know what, which one we were
You're
trying to
looking
get
for
to.
the value.
Right, because I mean, you could technically say head equals head.next down
Maybe
to
we should have made it alphabetical letters.
but you wouldn't actually do that, right? Like, but yes, that's yeah. I tell you what, I don't want to cut too much into our.
Would you run it as an if statement? If value equals 2?
If you would do that if you wanted to find one with that value, right, and then get rid of it. But if you wanted to get rid of just the second element, then you would just keep a counter and say, okay, am I at the second one? Okay. Then point the last one. But to do this, right, to get rid of something that's not the first one, what do you have to do in this list, right? Because you can't just say delete it, right? Because currently 1 is pointing to 2 and 2 is pointing to 3. Or, well, yes.
You have to rechange the reference from 1 to 3.
That's right.
And
That's
then 2
absolutely
will just go
right.
away.
That is absolutely right. So to do that, usually what you do is you create a previous, right? So you have your hopper that starts on the head, and what you do is you create a node that was called like last, right? And the idea is that every time that you go through this, you set last to whatever you're just coming from. And when you find the element that you're at, like 2, you just say, okay, well now last, this thing, last next, points to IT next, and you've now dereferenced. Now that thing no longer has any reference to the chain. Now it just goes 0, 1, 3, 4, so on and so forth. And again, think about how fast this is. Now traversal is slow because you're hopping down the list, but dereferencing that is way, way faster than trying to get rid of something, out of the middle of some other type of data structure. So use it where it is very helpful. And by the way, you other data structures are quite similar to this. Like if you do like a black-white tree, right? It has like some value, and then it has like a black and a right, or a left and a right. That's black and black-red trees, what they do. But that's the same thing. Same type of deal. You just now have 2 references, a right and a left. And then those nodes have a right and a left. So now you're doing like a binary tree. And again, binary trees are really, really fast. Because you think about it, if you come down a binary tree and it's not, if you get down to the second node and it's greater than some value, if you had 1 million elements, right, 1 million, because you cut it in half every time, it takes 20 hops. Now think about that. 1 million elements cutting out, being able to sort through that fast enough in 20 hops. Binary tree is really good. And we have some other data structures that are good. So this is one. Linked list is one. If anybody's interested just because I think I've heard people be confused about this, in other languages they have different names in different languages. In C# it's called list. A lot of people think that that is the same thing as a linked list. It is not. Actually, that is arrays under the hood. It's just doing a lot of the management for you. So when you have an array that's like, 50 elements and you want to add 51, what it will do under the hood is make an array of like 75 and then just keep up with you. That way you can add more without needing to increase your array. Same thing with the making it smaller. So it just does a lot of that management. But very, very fast to access. So lists are almost you're going to be always your go-tos, as opposed, unless you absolutely know that the amount of data that you're going to have is fixed. But yeah, you guys will.
So on a fixed array, if you were deleting one, would you then, like, say you had a 4 element array? Would you have to then create a 3-element array, copy just the 3 elements you're
If you wanted the link to reflect the amount of data that was in there, yes. Now you could delete.
So that's when you say it's expensive both to
very
add and delete
expensive.
is the exact
And think about. Okay, so we created 20 elements here, right?
Mm-hmm.
That didn't cost. Each one of those things cost us the same as what. But if we were doing that as an array, and we made here's an array of 1. And then we made it 2. It creates 2, copies that over, and now we have 2. 3, same thing. Very, very.
So is that what's happening under the hood in like JavaScript, where you don't have to set the array length?
Sort of. JavaScript is actually doing more of a list type thing.
Okay.
But also, throw JavaScript on any benchmark. Against anything, it's just so slow. Yes, but yes,
so the language is where you don't have to set the specify.
Right. And everything in JavaScript
is just handling it differently under
right.
the hood.
That's right. But it is learning stuff like this is important. In fact, April, if you remember, you did a solve for one of those problems that we did in the Slack channel, and it worked, right? It totally worked. But I said, well, hold on a minute, because understanding that search for an index on every one, that was a 600 element search, right? Like as opposed to just going to the element. So understanding stuff like this, even if you don't use it, is very important, because now you will understand some of those methods that you call on often. And you would think in JavaScript or something else, well, I don't know why this is taking so long. I ran the method, it did its thing, right? But if you understand what's going on under the hood a little bit, now you can kind of say, oh, well, this searches through every index of everything that I put in there. Sure, it spits out the answer that I want, but is there some more optimized way to do it? And if you ever want to code in anything that's not JavaScript, or like maybe Python or something, this is not a C# thing, right?
I understand that.
So
I understand
it's quite
that.
important. It's quite important.
But at the same time, for somebody like
structures.
myself who's newer to the concepts in general, like I'm not gonna know, that's a really costly thing, and
That's why
even if I do know that, I'm not always gonna know what the optimization would be.
But I think that's why it's important. That's important for you guys to learn this this type of stuff too. But anyway, I don't want to cut in too much to the networking thing. Does everybody kind of understand at least the idea of linked lists? So if somebody said, hey, what do you use a linked list for? Why wouldn't I want to use a linked list in this? Oh, well, for sort? Yeah, no, that's not a good idea. You're going to traverse every time you're looking for any element. It's very slow. And Doubly linked lists, they have, just to throw it out there, they also have circular linked lists. All that means is that the end points to the beginning, so that if you would infinitely cycle through, yes, exactly, and you maintain that.
It's only adding one end though.
That's actually adding 0 ends, because if your last element points to your first.
It's just the last one points to the first one instead of null.
Instead of null, that's right. And there's no way to know the end or anything. Yeah, but again, that would have its uses too. If you needed a constant circle of something, but still needed to be able to add elements, just because it circles doesn't mean you couldn't throw the 3 in between, the 5 and the 6. Right, exactly.
But there's no beginning and no end.
Right, and that can be useful. That's what I say, use case everything.
As long as you don't need to print
this is one of I think, honestly, this data structure is not too complicated. I think the only thing that throws people is when you do stuff like current equals current next. That kind of takes a little bit of thinking. You just have to like separate the two. Like this is a completely different object. Even though it's tacked onto this, it's pointing to a completely different object. And all I'm saying is, where this currently points, I want it to point here. But, yeah, you get the idea, I think.
You can't think of it like arrays.
That's right, you
If you
can't.
start-
And it's
that was
kind
my
of hard to
problem.
get yourself out of that.
When I asked you if there was a plus plus for it, because I was thinking of it like an array with the element
Right.
1, element 2, element 3,
Right.
when there's not. It's
Nope.
just element and then point to the
Yeah.
next element.
That's right. You guys did a wonderful job. I am quite proud of you, especially Tony.
What was, can you show the end of your, that void, the function you wrote?
Sure, well, it's the same thing that I had up there. It's just I didn't want to write it twice. It's just
All
something
day
I
I'm
just-
like,
I've never, it's
And now when I'm posting those challenges on Slack for linked list, you guys can do it. Yeah. Oh,
So how can I change the project name?
I find nothing on Slack that has been answered like 20 times already.
Once you make it,
I did a
you
few,
can,
'cause I was
but you're
thinking that.
gonna have to go into your config thing and change a whole bunch of stuff. It's kind of, you would be better off making a new project and just copying those classes in. But yeah, there's also the quick. You guys know you got Harlan coming in the 7th to do a C#. What's it? C# and web API, like a quick web API. He's coming in. Hopefully, at least maybe that'll help out a little bit with syntax as well. Cool. Man, you guys are great. Got in the room so many smart people. Woo.